Hello and welcome to this next lecture in the pattern recognition course. We have been looking at support vector machines idea. This lecture will close this, we will look at kernels in general. Just to recall, we have looked at the support vector machines both for classification and regression. The basic support vector machine that lands optimal hyperplane for a 2-class classification, and also seen how we can do support vector regression using epsilon insensitive loss function. And we also seen some generalizations of the basic SVM idea. For example, look at the new SVM, the SM, the way to add b square to the primal objective function, so that the dual becomes very simple to solve. Okay. So, which is called successive over relaxation SVM. So, we have seen some of the generalization of the basic SVM idea. So, to ultimately take some very broad look at what the SVM idea has added, there are essentially two important ingredients in the SVM idea. Okay. If I am looking at only classification, then as I told you, the power of the algorithm comes from the fact that we are learning optimal hyperplane, which is what allows us to learn a classifier with very low true risk, and by using kernels to do inner products, we are able to learn a nonlinear classifier with a linear this thing. But if I look at everything, all the SVM type ideas, so essentially kernels is one important idea. An equally important idea, which is what allowed us to use the kernel idea in the first place, is that the final function admits a representation in terms of kernel functions, right. So, we see in, for example, in the SVM, the final W is a linear combination of data vectors, and hence the final classification function, the discriminant function, can be expressed as a linear combination of kernels, of kernel function values. Okay. So, we can call this as support vector expansion. So, representing your final classifier, say final classifier function f x, where sin of f x will be your classifier, representing that function f x as a nice kernel expansion. Okay. So, we will call that support vector expansion. So, these two are the two ingredients that allowed us to solve nonlinear problems using linear techniques. Now, both these are much more general than what we have seen in the simple SVM method, right. Kernel functions in general allow us to learn nonlinear models using linear techniques, and are also a very good way to capture similarity that is useful in a general way. So, kernel functions can be thought of as capturing similarity or dissimilarity between feature vectors. Okay. In the same way, support vector expansion is also a very general property of kernel based methods, right. So, what we will do in this class is to look at this general overview of kernels. Okay. So, what I will do is I will first give you a very brief introduction or brief idea of what we mean by kernels are a good way to capture similarity, and then we look at positive referential kernels in a little more detail to understand the kernel idea in a slightly more general fashion than what we have seen so far. Okay. In pattern recognition, we always use distance as a means to assess similarity, right? That is one of the ways in which you can do this. At the beginning of the course, we looked at what is called nearest neighbor classifier. Nearest neighbor classifier, I store some prototypes, and when you give me a new pattern, I find the distance, the Euclidean distance of the new pattern to each of the prototypes. Whichever prototype is closest to, I will put that in that class, right. We have seen that is an interesting, very simple classifier, and if I have sufficiently many prototypes, its worst case probability of error is at worst twice that of the base error. So, in that sense, for a simple classifier, it does remarkably well. Right. Now, kernels allow us to generalize such notions, right. So, the basic idea there is if two patterns are close to each other in a distance sense, then there are also similar patterns, right. So, the question is what kind of distance is a good distance. So, we may have some similarity function which we can think of as a kernel, and then we can use the kernel in place of the usual distance. Okay. We'll look at this with a very simple example to see how kernels can be used in a nearest neighbor classifier. So, for the example, let us take as usual a 2 class classification problem. Let us say xi yi, that is x1 y1 xn yn are the samples, and the classes are +1 -1, and the feature vectors are in Rm. Now, suppose we implement a nearest neighbor classifier by computing distance from a set of prototypes, and the whole idea is that what does the SVM idea amount to, that we do not do it in the original feature space, but we map the feature vectors to some other high dimensional space and do distances there. So, the same way we are using some phi to map x's, and we are actually finding Euclidean distance or distance using a inner product in the range space of phi. Okay. So, let us say we use only 2 prototypes, we call them C plus and C minus. C plus is 1 by n plus summation of phi xi, where I is such that yi is +1, that is nothing. So, n plus is the number of examples of class +1, similarly n minus is the number of example class -1. So, this is nothing but the average of all the patterns of class 1, not in the original space, but in the range space of phi, because I have mapped the original feature vectors using phi to some other space. In that space, C plus is the center of all the class +1 examples. Similarly, C minus is the center of all the class -1 examples. So, these are the 2 centers of the 2 classes. So, we use them as the prototypes. The idea is that if you give me a new x, I will go to the range space of phi. So, I will find the distance between phi x and C plus. This is phi x minus C plus norm square. If that is less than phi x minus C minus norm square, then I put it in class +1, otherwise I will put it in class -1. This is a simple nearest neighbor classifier with 2 prototypes, but distance is not found in the original feature space, but in the phi space. Okay. Now, we can do all this using kernels as follows. So, basically we need to look at this phi x minus C plus whole square, right, that is the distance. By expanding phi x minus C plus whole square, it becomes phi x transpose phi x minus 2 phi x transpose C plus transpose C plus. Now, I want phi x minus C plus whole square greater than phi x minus C minus whole square. So, do the simple algebra, this constant term cancels both sides. So, finally, it means we will put x in class +1 if this quantity is greater than 0. Phi x transpose C plus minus phi x transpose C minus plus some constant which is C minus transpose C minus C plus transpose C plus. So, basically I have to do all these inner products to be able to implement my nearest neighbor classifier by first transforming all the patterns using the function phi. But the idea is that all these inner products can now be kernelized, right. Very easy to see that they can be kernelized. What is phi x transpose C plus? Phi x transpose, this is my C plus, right. Now, push phi x inside, then it becomes phi x transpose phi xi, which is nothing but k x I x. In a similar way, what is my C plus? My C plus is this. If you want C plus transpose C plus, what you will ultimately get is phi xi transpose phi xj for all ij pairs such that both yi and yj are +1. And phi xi transpose phi xj is k xi xj. So, I get C plus transpose C plus like this. Similarly, I can write C minus transpose C minus, which means finally, my nearest neighbor classifier is sign of Hx, where Hx can be obtained like this. This is phi x transpose C plus, this is phi x transpose C minus, and the constant B is this C plus transpose C plus minus C minus transpose C minus. Right. So, everything can be kernelized. So, what it meant is that I can, for example, use phi to transform my features into some other high dimensional space and find the actual distances there. So, if I have a suitable kernel, right, then I can actually implement nearest neighbor classifier by implicitly transforming features into a high dimensional space, right. Now, another way of looking at it is essentially the kernel captures. So, if I think phi x transpose whatever norm of phi x minus phi y is a good metric for distance between pattern vectors x and y, then correspondingly k x y is a good similarity measure. Okay. So, that we can implement such nearest neighbor classifiers by implicitly transforming the feature space, and the kernel function allows us to formulate the right kind of similarity measure in the original space. For example, if I am using a Gaussian kernel, so which means that I measured similarity over some spatial extent by tweaking my sigma parameter and so on. Okay. Another way of looking at it is, suppose I take this what we call phi x transpose C plus and phi x transpose C minus. I call them P plus x and P minus x. Now, these are very familiar expressions, right. This is summed over all the examples of one class, some kernel functions. So, there is some function defined here, its value at x is summed over all examples of class plus 1, the kernel functions at each of the example points, right. This x is same as this x, that is the argument. So, if for example, this was a proper window function, this is nothing but a non-parametric estimate of density. For example, if I take this to be Gaussian, which means I am putting a Gaussian centered at each of the x's and sum up and sum up all their contribution to x, that is my estimated class conditional density at x. Right. So, with the proper normalization, these are nothing but non-parametric estimates for class conditional densities, the kernel density estimates, right. So, we have seen the kernel density estimates, and my final classifier is if p plus x minus p minus x is greater than something, right. So, all it means is that no, these are nothing but non-parametric density estimators that we have seen earlier, right. These are the kernel density estimators, and in that sense, what I call the nearest neighbor classifier using kernels is like a base classifier using a non-parametric density estimator for class conditional densities using the kernel, a properly normalized kernel for the density estimation. So, in this sense, once again you can see kernels give us some kind of a similarity metric. Okay. All right. Now, let us look at a few more general theoretical details of kernels. We defined positive definite kernels earlier. We actually looked at two different kinds of definition of kernels. One are positive definite kernels, other are kernels that satisfy Metzger's theorem. We just said that anything that satisfies Metzger's theorem is such that there always exists a phi, and k x comma x prime will be phi x transpose phi x prime. Okay. We didn't prove this theorem, but for positive definite kernels in this class we will show that there always exists such a space, and we actually construct this space. Okay. So, we look at positive definite kernels in some detail, because these are one of the most important kernels for pattern recognition today. So, we will show that for any such kernel there is one vector space, we will call that H, script H, which has an inner product on it. So, a vector space endowed with inner product that we can construct, so that the kernel is an inner product in that space. So, this particular space is called the reproducing kernel Hilbert space RKHS associated with this kernel K, and we will actually show how to construct this space. And then we also show that if you are doing regularized empirical disk minimization under almost any loss function, then the final solution would have a support vector expansion form. Okay. The rest of this lecture assumes some level of mathematical sophistication. Specifically, I am going to assume that everybody knows general vector spaces, norms, bases, orthogonal vectors, orthogonal complements of subspaces, and so on and so forth. So, if any of you do not know any vector spaces, maybe it will be a little difficult to follow the rest of the lecture. On the other hand, the rest of this lecture is independent of the course. So, if you do not understand the rest of the lecture, can just skip it. Okay. So, let us start looking at positive definite kernels. as earlier, let x be the original feature space, the script x, and k is a positive definite kernel, that is k is a symmetric function on x cross x, a real value symmetric function x cross x, which which satisfies some conditions. Just to recall that, given any n points, let us say x1, given any n and n points x1, x2, xn in by feature space, the n by n matrix whose ijth element is k xi xj is called the gram matrix of k. So, if I take all the xi xj's and arrange them as n by n matrix, it will be a symmetric matrix, and recall that k is a positive definite kernel. If the gram matrix is positive semi definite, that is its quadratic form is always greater than or equal to 0 for all n and all points x1 to xn. Okay. This is what we defined earlier. So, specifically because the quadratic form has to be greater than or equal to 0, a positive definite kernel, if k is a positive definite kernel, then for every n and every x1 to xn, the summation over I and j going from 1 to n, ci cj k xi xj, this is the quadratic form of the gram matrix, is greater than or equal to 0 for all scalars ci. Okay. So, given any scalar c1, c2, cn and any element from my feature space x1, x2, xn, this double summation I j going from 1 to n, ci cj k xi xj has to be greater than or equal to 0 if k has to be a positive definite kernel. Okay. For this talk, we are going to confine ourselves to all our scalars being real, even though everything that we say can be extended to the scalars coming from the complex field, we will restrict ourselves to scalars being all real numbers. Okay. So, what does this mean? Once again, this is nothing but the gram matrix, n by n gram matrix is positive semi definite. If I take n is equal to 1, of course, the matrix has only one element. So, which means k x comma x should be greater than or equal to 0, positive semi definite. If I take n is equal to 2, it will be a 2 by 2 matrix. The first row being k x1 x1 k x1 x2, second row will be k x2 comma x1 k x2 comma x2. We want that to be positive semi definite, which for example mean that the determinant has to be greater than or equal to 0. So, if I take n is equal to 2 and I take the determinant will be k, the main diagonal is k x1 x1 into k x2 x2, off diagonal is x1 x2 into x2 x1, but k is symmetric. So, the determinant has to be positive. So, k x1 x2 whole square should be less than or equal to k x1 x1 into k x2 x2. This is true for every pair of features x1 x2. So, if k is a positive definite kernel, then in particular it satisfies this. Given any two feature vectors x1 x2, k of x1 comma x2 whole square is less than or equal to k of x1 comma x1 into k of x2 comma x2. I hope all of you recognize the structure of this inequality. This is nothing but the Cauchy-Schwarz inequality, because we think of k as a inner product. If k was indeed an inner product, obviously phi x1 transpose phi x2 whole square is less than or equal to phi x1 transpose phi x1 into phi x2 transpose phi x2. But we have not yet shown that k is actually inner product. We just defined that a symmetric function to be positive definite kernel if it satisfies this. But it satisfying this means that this kind of Cauchy-Schwarz inequality is satisfied by the kernel. Of course, the Cauchy-Schwarz inequality does not mean that there is a space in under function phi that k x comma x1 comma x2 is phi x1 transpose phi x2, but certainly the function k, by virtue of it being a positive definite kernel, satisfies the Cauchy-Schwarz inequality. Okay. This is going to be very important for us later on in the in studying positive definite kernels. Okay. If in fact the kernel is obtained as an inner product in some other space, that is, if script x can be mapped to some other space using phi and the range space of phi has an inner product, here I represented the transpose. So, in fact, if k x comma x prime is phi x transpose phi x prime, then that such a k is certainly positive definite. Why? Because for k to be positive definite kernel, I want to show that this ci cj k x xi xj should be greater than or equal to 0. K xi xj is nothing but phi xi transpose phi xj. So, I need to show ci cj phi xi phi xj transpose phi xi transpose phi xj is greater than or equal to 0. Now, this can always be written as summation over I ci phi xi transpose summation over j cj phi xj, these two are same element. So, this is nothing but norm of summation over I Ci phi xi, norm square of that. So, this is always positive. Okay. So, if in fact K happens to be an inner product, then K will always be positive different, right. But we only ask this for positive differentness, and this is of course much easier to verify than your Mercer's theorem. So, thus if K satisfies Mercer's theorem, then we know that there is some phi and K can be written like this. So, if K satisfies Mercer's theorem, there is a positive different kernel. Okay. Now, we show that all positive different kernels are also inner products on some appropriate space. As I said, we show this by saying given a kernel K, we will construct a space endowed with the inner product and show how any positive different kernel is essentially implementing an inner product in this space. As I said, this space is called the reproducible kernel Hilbert space. So, to start on this, let R superscript script x, right, this one, let this be the set of all real valued functions on my feature space. That is, if I have any function g that maps my feature space to real numbers, then that g will be an element of this set. So, this set consists of all possible real valued functions on my feature space x. Okay. Now, K be the given positive different kernel. So, given any element x in my script x, any feature vector x, let us represent by K dot comma x. This is general representation for functions. The dot is where the function's argument is. So, essentially this is a function, because you put anything in place of this dot, you get a real number, and thing that you can put in place of this dot are elements of script x. So, K dot comma x is nothing but a function that maps script x to real numbers. So, this belongs to R superscript x, right. So, K dot x is some real valued function. Let us say this denotes the function that maps any x prime to K x prime comma x, that is almost different. So, simply dot is the notation for the dummy argument of the function. So, K dot comma x is the real valued function on x, whose value at an argument x prime is K of x prime comma x. Now, consider the set of functions h1, which consists of all such K dot x's for every x in my feature space. Actually, we can think of K dot x as the kernel function centered at x, because actually this now is actually a function. Okay. Its value at any argument value is the value of the kernel function x prime comma x. So, this we will call this a kernel centered at x. So, h1 is the set of all kernel centered at all possible feature vectors, all possible elements of x. Okay. Let script h be the set of functions that are finite linear combinations of functions in h. So, you take h1 and make finite linear combinations, let us say alpha 1 k dot x1, alpha 2 k dot x2, like that. So, all possible finite linear combinations of functions of h1, right. If you take all possible finite linear combinations of functions of h1, let us call that set of functions as script h. Okay. So, script h is the set of all functions that are finite linear combinations of functions in h1. So, any f in h would be a linear combinations of functions from h1, and the only functions in h1 are k dot x types, where x is an element of script x. So, any f in my script h can be written as alpha I k dot xi for some n. So, it is a finite linear combination. So, we do not know how many terms there will be, but there will be some integer n such that there will be n terms in the linear combination. So, f will be I is equal to 1 to n for some n, alpha I k dot xi for some real numbers alpha I and some xi. So, every function in the script h can be written like this. For some x1 to xn elements of script x, some alpha 1 to alpha n real numbers and some n, f can be written as I is equal to 1 to n alpha I k x. Which means, if I have two functions f and g in h, it is very easy to say f plus g is also in h, because f plus g would once again be some finite linear combination of k dot x's, right. And similarly, alpha times f will also be in h for any real number alpha, which means h is a vector space over the field of reals, right, because the rest of the vector space axioms are easy to verify. Essentially, we have a vector addition and scalar multiplication well defined. So, this set H now is a vector space under the usual addition of functions and scalar multiplication functions, a vector space over the field of real numbers. As I said, everything I say in this lecture can be extended to the field of complex numbers with minor modifications, but for simplicity we will stick to all scalars being real. So, what we showed is that if we take finite linear combinations of kernels centered at any points in X, okay, if we call that the space H, that H is a vector space under the usual function addition and scalar multiplication. So, now what we are going to do is that we define an inner product on the space H, okay, inner product, and then show that essentially there can be a phi that maps script x to this H. So, that k x comma x prime will be phi x prime inner product that we are going to define. Okay. So, first I have to define an inner product for any two elements of H. So, let us take any two elements of H, f and g. Every element of H is a finite linear combination of kernel functions centered at xi. So, f is summation I is equal to 1 to n alpha k dot xi, alpha I k dot xi for some reals alpha I, some elements xi. So, g is beta j k dot xj prime. So, x1, x2, xn, x1 prime, x2 prime, xn prime prime, these are all arbitrary. I took n and n prime also different because the two functions may have different number of terms in their linear when they are represented as linear combinations of case. So, given two functions f and g like this, we will define the inner product. I am going to represent the inner product like this. In general, the standard notation for inner product between the two angular brackets f comma g within the angular bracket. So, this is the inner product of f and g. If f is this and g is this, we will represent the inner product of f comma g as I is equal to 1 to n, j is equal to 1 to n prime summation alpha I beta j k of xi comma xj prime. Okay. So, if f is this and g is this, then the inner product is defined to be this. Of course, you have to show that this is an inner product, it has satisfy all the properties of the inner product. But before we can go there to show that this is an inner product, we have to first show that this is well defined. What do you mean by well defined? When I say elements of H are finite linear combinations of elements of H1 which are nothing but kernel functions centered at points x. Okay. So, this function f given different arguments, say f of x is alpha I k x comma xi. Right? Now, so given a function f in H, there may be more than one way of writing it as a linear combination of some kernel function. Right? When we say we take all possible linear combinations, there is no guarantee that two different linear combinations do not give you the same function, which in other words, a given function may not be representable uniquely as a linear combination, which means these alpha i's are not sacrosanct. The function of course is sacrosanct because function is an element in H, but the same function may be representable with some alpha I primes of and some k y i's, who knows. Right? So, so essentially what we have to show is that it is not dependent on these alpha i's and beta j's, right, because they can be different kinds of representations. So, the inner product should not be dependent on the expansion coefficients. Okay. So, first let us show that it does not depend on the expansion coefficients. The inner product as we define, now I can take alpha I outside, what I have is j is equal to 1 to n prime beta j k xi xj prime, g dot is j is equal to 1 to n prime beta j k dot xj prime, right. So, g of xi will be beta j k xi xj prime, right. So, if I take alpha I out, what I have is beta j k xi xj prime, which is nothing but g of xi. So, I can write the inner product as I is equal to 1 to n alpha I g of xi, which means while it depends on the function g, it does not depend on either beta j or xj prime, right. If G can be written in different ways, it does not matter as long as it is the same function. It only depends on the values of G at xi, right. So, if G has a different expansion, it does not matter. Similarly, by taking beta j out, by interchanging the two summations and taking beta j out, I can write as j is equal to 1 to n prime beta j is equal to 1 to n alpha I k xi x j prime. What is this? F dot is this. So, f of x j prime will be I is equal to 1 to n alpha I k of x j prime xi. Anyway, k is symmetric. So, whichever way I write it does not matter. So, this entire summation is nothing but alpha of x j prime, I mean f of x j prime. So, I can also write f the inner product between f and g as summation j is equal to 1 to n prime beta j f of x j prime. So, it depends on the value of the function f at x j prime, but it doesn't specifically depend on the specific vectors xi or alpha I, right, which shows that the inner product does not depend on the specific expansion coefficients, and hence it is well defined. Okay. So, this is a well defined inner product. So, next we have to ask, is this indeed an inner product? I just said this is an inner product, we have to show that this is an inner product, right. So, what does an inner product satisfy? An inner product on a vector space H takes pairs of vectors and gives you a real number, right. So, it is a function H cross H2 reals. What does this function satisfy? It has to be symmetric, it has to be bilinear. Inner product of any element with itself is always greater than or equal to 0, and inner product is 0 if and only if the element is 0. Inner product of some element with itself is 0 if and only if the element is 0. These are the properties of the inner product. Now, our inner product is symmetric by definition, right, because this is how we define this. So, given this and this does not depend on which is f and which is g, because this alpha I beta j k xi x j prime and k is symmetric. So, inner product of f and g is same as inner product of g and f. I would like to remind you once again that we are considering field of real numbers. Our vector space is vector space over reals. That is why we are only looking at symmetry. Otherwise, we have to worry about complex conjugateness, but we are not allowing complex scalars right now. For simplicity of exposition, I am just taking everything to be real. Okay. Similarly, it has to be bilinear. The inner product of f g1 plus g2 should be inner product of f comma g1 plus f comma g2. Similarly, the other way, which is also very straightforward because of the definition of the inner product, is very easy to verify that it is bilinear, right. So, if I put f1 plus f2 here, so I will get some alpha I k dot xi plus some gamma j k k dot some x bar j. So, accordingly they come in the summation. So, f1 plus f2 comma g will be f1 comma g plus f2 comma g and so on, right. So, by definition it is symmetric and it is bilinear, and similarly you can show that if one of the arguments is multiplied by a constant, the inner product gets multiplied by that constant. Next, what do you have to show? We have to show that inner product of f comma f is greater than or equal to 0. What is inner product of f comma f? If f is alpha I k dot xi, inner product of f comma f is alpha I alpha j k xi comma xj, some more I j. So, this is nothing but the quadratic form of the Gram matrix, and because k is positive different kernel, this is greater than or equal to 0. So, we have also shown that inner product of f comma f is greater than or equal to 0. So, the only thing that remains to be shown now is that if the inner product is 0, f is 0. Mind you, if I had assumed, if I defined positive definite kernels as a function k such that the Gram matrix is positive definite rather than positive semi definite, then I am done. If I am asking for this to be positive definite, then except when all alpha I alpha j 0, which means function is 0, this quadratic form has to be strictly greater than 0. But if I want positive definite functions only, then it will be very difficult for us to get kernels, because we want kernels to represent similarity in general. As it turns out in many applications, well, it is easy enough to show Gram matrix is positive semi definite, it is much more difficult to show that Gram matrix is positive definite. So, we do not want to assume positive definiteness of the kernel because we do not need it, right. So, I just want you to understand that because we assumed only positive semi-definiteness of the gram matrix, I only get f comma f inner product of f and f is greater than or equal to 0, and is not I still have to separately show that if inner product is 0, f is equal to 0. So, let us go ahead and show this separately. Show this, let us take some p functions from H and some p scalars gamma 1 to gamma p, and let G 1 is gamma fi, because H is a vector space, G will also be in the in H. Now, if I look at gamma I, gamma j, fi fj, gamma I, gamma j, inner product fi fj, sum dot I j is equal to 1 to n, right. By the bilinearity of the inner product, it is same as inner product of I is equal to 1 to p gamma fi, comma j is equal to 1 to p gamma j fj, right, because of the bilinearity of the inner product. We see that inner product of f1 plus f2 comma g is inner product of f1 comma g plus f2 comma g, and similarly the other way, and hence this summation, Z double summation can be written as inner product between these two. Now, this is nothing but what we call the function G1. So, this is nothing but the inner product between G1 and G1, because these two are the same summation, I and j are dummy variables after all, and this we already shown to be greater than or equal to 0. Okay. So, what it means is, given any p functions from H, f1, f2, fp, and any p scalars gamma 1, gamma p, gamma I, gamma j, inner product fi comma fj, sum dot I j equal to 1 to p is greater than or equal to 0. What does this mean? This is exactly what we wanted from a positive definite kernel. Earlier positive definite kernel meant, as we seen, ci, cj, k, xi, comma xj is greater than or equal to 0. So, I can think of the inner product itself as a kernel on H. Our original k, the kernel I am considering k, is a kernel on script X or feature space, but now it looks like fi fj can, what is fi fj? Fi fj, this inner product is a symmetric function that maps H cross H. The inner product is given any two elements of H, it maps it to a real number and the function is symmetric, and any such symmetric function, by virtue that it satisfies this, mean that it is a kernel on H. Okay. So, that is what we have shown is that this function, the inner product function, which maps H cross H to R, is in fact a positive definite kernel on H. Because the positive definite kernel on H, we know that positive definite kernel satisfy Cauchy-Schwarz inequality. What does the Cauchy-Schwarz inequality mean? The kernel value at x1 comma x2 whole square is less than or equal to kernel value at x1 comma x1 into kernel value at x2 comma x2. So, if I take any two elements from H, their inner product square, so this is element 1, this is element 2 square is less than or equal to inner product of element 1 comma element 1 into inner product of element 2. So, in particular, I know that if I choose f as one element and k dot x as another, then because it satisfies Cauchy-Schwarz inequality, we now have inner product of k dot x comma f whole square is less than or equal to inner product of k dot x comma k dot x and inner product of f comma f. So, let us calculate each of these inner product from our definition of inner product. Recall that if f is equal to alpha k dot xi, g is equal to beta j k dot xj, then inner product of f comma g is this. So, what does it mean? For example, if I want k dot x comma k dot x prime, right, then both of these sums are only one element sums, both these expansions are one element expansion. So, my f comma g will be nothing but k of x comma x prime, right. So, k dot x comma k dot x prime is k x comma x prime. Similarly, if f is this, but g is simply k x prime, one element, then what will be the inner product? Alpha I k x prime comma x I. Right? So, if g is simply k x prime, then the inner product will be summation alpha I k x prime comma xi, which is nothing but f of x prime. Right. I hope this is clear. K dot x comma f is f of x. It is a very, very important property. Right. Just for our definition of inner product shows this. Right. Let us understand this again. Let us say f is this alpha I k dot xi, sum over I, and let us say g is simply a single function k dot x. Then what will this double summation be? Simply a single summation I is equal to 1 to an alpha I k x comma xi. Now, summation alpha I k x comma xi is nothing but f of x. Okay. So, our definition of inner product is such that k dot x comma f is f of x. Now, this is called the reproducing property of the kernel. If I take a kernel centered at x and take its inner product with f, what I get is the value of f at x. Right? If I take a kernel centered at x and take its inner product with f, then what I get is the value of f at the x. This is called the reproducing kernel property. Because the reproducing kernel property, what we have is the following. Now, f x square, which is nothing but the inner product of k x comma f whole square. By Cauchy-Schwarz inequality, this is inner product of k dot x comma k dot x, which is nothing but k x x into inner product of f comma f. Okay. So, what does that mean? It means if f comma inner product of f comma f is 0, then for every x f x whole square is 0. That means, for every x f x is equal to 0, that means f is equal to 0. So, we have shown that our inner product is such that if inner product of f comma f is equal to 0, then f is identically equal to 0, okay, using this so called reproducing kernel property. So, this shows that what we defined is indeed a proper inner product. Okay. So, given any positive definite kernel, we can construct the inner product space H as explained, right. You give me a kernel K and I have the feature space X. I take kernel centered at each point on x, which what we call k dot x. We take the set of k dot x for every x, for x in my feature space. Then I make all possible finite linear combinations of these kernels alpha I k dot xi summed over I, and I construct the set of all such functions, that is my space H. This space happens to be a vector space on which I can put an inner product, and once I put this inner product, technically I want this space to be complete. What do I mean by complete? That an inner product obviously gives me metric, right. If I have an inner product between two elements f comma g, then I can have a norm for f as norm f square is inner product f comma f, and I will define the distance between f and g as norm of f minus g, right. Under such a distance metric, if any sequence is Cauchy, that is a sequence that as n and m tend to infinity, the nth and mth element of the sequence come close to each other in the distance metric, then the sequence should also have a limit, right. That is what is meant by complete. If a space is not complete, we can always complete it. This is just a technical digression. If you do not understand, it does not matter. Essentially, H is a vector space with inner product, and we simply assume that under this inner product all convergent sequences have their limits in the space. Okay, that is what is called completing the H. This space is called a reproducing kernel Hilbert space. Essentially, Hilbert space is a vector space on which you define an inner product, and in the metric induced by the inner product, the space is complete. Okay. So, that is why it is called a Hilbert space. So, this H that we constructed is called a reproducing kernel Hilbert space, and the reproducing kernel properties. So, given a positive kernel K, we constructed the H, on that H there is an inner product, and the inner product is such that inner product of k dot x comma f will give me the value of f at that x. This is called the reproducing property of the kernel. Okay. This is true for every f in the space. Okay. Essentially, the elements of this RKHS are real valued functions on x, not all real value functions of certain kinds of real value functions of x, which can essentially be written as linear combinations of kernel centered at x. So, this is a kind of generalization of linear functionals on X. Right? So, that is another way of looking at RKHS, which have essentially this special reproducing kernel property. So, given this RKHS H with associated with K, now we can define a phi that maps X to H, that maps every element of X to an element of H. Namely, I map the element X in my feature space to the element K dot X in H. I map X to the kernel function centered at X. Right? So, phi maps X to K dot X. If I take this phi, then the inner product of phi x comma phi x prime is nothing but inner product of K dot X comma K dot X prime, which is nothing but K x comma X prime. So, K x comma X prime is nothing but inner product between phi x and phi x prime in H. So, H is the space you are looking for. Given a Pointer kernel K, now I have constructed a specific space H and I showed you a function phi that maps X to H, such that K x comma X prime is nothing but inner product between phi x and phi x prime. Right? So, this means that any Pointer kernel gives us an inner product in some other space as needed. Okay. Now, let us just get a little more idea of what this RKHS is. In a very familiar setting, if you look at it, then we may get some more idea of what this RKHS is. So, we will look at a very simple example. Let us assume X is Rm and let us take the simplest linear kernel K x comma X prime is X transpose X prime. So, what will be K dot X now? K dot X is a function that takes dot product of its argument with X. For each X, I have a function K dot X, which is essentially taking inner dot product with X, that is the name of the function. So, you give X prime as the argument of the function, out comes X prime transpose X. So, essentially K dot X is the function that takes dot product of its argument with X. So, let us take any vector X in Rm with components x1 to xm and let us say ei or the coordinate unit vector, that is E1 is 1 0 0 0, E2 is 0 1 0 0 and so on. If you give me any x prime belonging to Rm now, K x prime comma X is by definition X transpose X prime. X transpose X prime is nothing but summation of over I of ith element of X and ith element of X prime. So, summation over I can write as Xi and I can get ith element of X prime as Ei transpose X prime, because Ei is the coordinate vector. Now, by definition of kernel, Ei transpose X prime is nothing but K of X prime comma Ei or Ei comma X prime, does not matter whichever way I write, but so summation Xi K of X prime transpose Ei. So, K x prime comma X is nothing but summation I is equal to 1 to m Xi K x prime comma Ei. What does that mean? K dot comma X is I is equal to 1 to m Xi K dot comma Ei. So, for any arbitrary X, if you want a kernel function centered at X, that itself can be written as a linear combination of these m specific kernel functions K dot Ei. That means, every K dot X can be written as a linear combination of K dot Ei, which means any linear combinations of K dot X for all X for different X's can once again be rewritten as a linear combination of K dot Ei, right, which means all functions in H are simply linear combinations of K dot Ei, and for I is equal to 1 to m, there are only m such kernel functions, and every other function H can be written as linear combination of this, which means any f can be written as I is equal to 1 to m Wi K dot Ei. So, any f can be represented now by m Wi's, which means it can be represented by a vector in Rm, which means every f can be uniquely defined by a m component vector, which means my RKHS itself is isomorphic to Rm, right, and that means every element in H can be associated with a hyperplane on X. So, my for my linear kernel, the reproducing kernel Hilbert space is nothing but the set of all hyperplanes on X. That is what a linear classifier gives me. Essentially, if I take the linear kernel X transpose X, then what I am doing is I am searching over hyperplanes over X. So, I am actually searching over the RKHS. So, the inner product in H now is simply the usual dot product in Rm, and learning hyperplanes is nothing but searching over this H for a minimizer of the empirical risk. Okay. So, we have shown the following. Given a positive definite kernel, there is a vector space with an inner product, namely the RKHS associated with K, and a mapping phi from X to H, such that the kernel is an inner product in H. The RKHS represents a space of functions where we can search for the empirical disk minimizers, is essentially that kind of functions. Now, given this, we will just do one very important insight, which is called the representer theorem. Okay. What does the representer theorem say? Let K be a positive definite kernel and H be the associated RKHS, and Xi, Yi be the training data set as earlier. Now, given any function f, suppose I want empirical disk under this training data set. So, empirical disk depends on some loss function L of yi comma f xi whatever. So, no matter what the loss function is, the empirical disk ultimately depends on what xi, yi, f xi for I is equal to 1 to n. It can't depend on anything else. Given these training examples and a function f, the empirical disk can depend only on xi, yi, f xi for I is equal to 1 to n. So, let us write empirical disk of any function f as some function c of xi, yi, f xi, I is equal to 1 to n. Right? So, we do not have to worry about what our loss function is. Let us say we want to minimize such a empirical disk, but we want to do a regularized empirical disk minimization. That means, we use a regularization term for which we use the norm in the H space, and let us say the inner product f comma f will represent as norm f square like this. Okay. So, this is the theorem. Let omega be any strictly monotonically increasing function. Then, if G is any minimizer, if I am searching over the RKHS and G is the minimizer of the regularizer risk, where regularizer risk is this empirical risk under any arbitrary loss function, plus the regularization term omega of which is a function of the norm of G in H. So, essentially the regularization term should be some increasing function of the norm of G. Okay. So, if I am using the norm of G in H as the regularizing under not direct norm of G, any increasing function of norm of G would do, then any minimizer can be represented as a linear combination of kernels centered at xi. So, G dot is alpha aka xi dot. So, the final minimizing function can be simply written as linear combination of kernel functions centered at data points xi. Okay. Let us see what it means. Functions in H are linear combination of kernels centered at all points of x. There may be uncountably infinitely many points in x. So, that many functions are there in H. Though we are searching over the space, the minimizer can always be expressed as a linear combination of kernels centered at data points only, and there are only finitely many data points. Which means, though H may be infinite dimensional, we can solve the optimization problem by searching for only n real numbers alpha I. I do not have to worry about what the G's representation is. My minimizer G always has representation like this, where xi's are all given. So, my G dot is nothing but alpha aka xi dot. So, essentially I need only alpha 1 to alpha n to find my G, my minimizer. Even though H contains linear combination kernel centered at all points of x and H may be infinite dimensional, I can find the minimizer by searching for only these n numbers alpha. This is essentially what we did when we solved the dual in SVM, right. Irrespective of the, as I said, of the dimension of the transform feature vector, the dual is dimensionality equal to the number of examples. Now, this is a very generic property when we work with kernels. If you are doing a search over the RKHS for a minimizer of the regularizer risk under any loss function, as long as the regularizer uses the norm of the function in H. Okay. So, let us quickly prove the representer theorem. In the vector space of H, consider the span of the functions k x1 dot x2. So, take the kernel centered at each of the n data points and take the linear span, that is a subspace. So, because this is a subspace, given any f in my RKHS, that f can be resolved into that component which is in this subspace and the component that is orthogonal to it. Let us call these two components f parallel and f perpendicular, which means for any f in H and any x in x, because f can be written as f parallel plus f perpendicular, f x is f parallel x plus f perpendicular x. F parallel x is what? With that part of f which is in the linear span of xi. That means, f parallel x can be written as a linear combination of k xi dot. So, f parallel x is nothing but I is equal to 1 to n alpha I k xi x for some alpha i's and f perpendicular x. What can I say about f perpendicular x? Firstly, it is also in H, and secondly, it is orthogonal to this. That means, its inner product with this with f parallel should be 0, and by bilinearity, its inner product with each of the k xi dot should be 0. For if xi's are the data points, then f perpendicular is the function such that f perpendicular comma k xi dot is equal to 0 for I is equal to 1 to n. This is true of every function. Given my data points x1, xn, I can resolve every function as the parallel and perpendicular components of this k of the linear span of k xi dot, and hence this kind of decomposition holds. Since H is RKHS, representation kernel property gives me f x prime is f comma k x prime dot, right. The inner product of f and k x prime dot is the f x prime, which means if I take any data point x j, f x j is the inner product of f and k x j dot. F is f parallel plus f perpendicular k x j dot. By bilinearity, this is f parallel inner product f x j, k x j, and f perpendicular k x j. F parallel k x j inner product can be written like this: f perpendicular k x j is 0, which means for each of the data points, f x j is same as f parallel x j. This is true for every function f in H. Now, let G be any minimizers of the regularization list. We can write G as G parallel plus G perpendicular, and hence we know G x j is G parallel x j for all data vectors x j. Now, the empirical risk only depends on xi, yi, g xi. So, it depends on values of g's only on the data points. On the data points, g and g parallel are same. So, the empirical risk of g will be same as empirical risk of g parallel. Okay. So, we know that empirical risk of g and g parallel are same. Now, let us look at the regularization term. So, we know norm g square is norm g parallel square plus g perpendicular square. These two are orthogonal, and so hence is greater than g parallel square. So, which means the omega of g square, g norm square is greater than omega of g parallel square, which means g parallel cannot have a regularized risk any more than that of g. That means, g parallel is also a minimizer of risk, right, and hence my minimizer always admits this representation. So, apart from the proof, this particular theorem is very important. It shows that essentially my minimizer, if I am doing empirical risk over empirical risk minimization and any loss function over the RKHS using the norm of the function under H as the regularizer, then it has this nice support vector expansion. Okay. So, this is a very generic property of all kinds of kernels, as long as kernels are positive different. That is the reason why one looks at positive different kernels. Okay. So, we will stop about the kernel based methods here. So, next class we will just round up what all we have done about learning nonlinear classifiers, and then move on to a few special topics to wind up the course. Thank you.